All right, everybody. Good afternoon again. It's time to get started. So let's see what you remember with writing equalities and conversion factors. So I will admit, I wrote this question when I was pregnant with my last child and certainly had a craving for Chick-fil-A. So I was like all about it. Didn't have any when I was pregnant, but I so wanted it. It was during the vid and I was like, I ain't getting no takeout. So that is where this question came from. You're like, what is up with her and Chick-fil-A? Is she okay? I'm okay. I just had a craving. So you're waiting in line at Chick-fil-A. Oh, I see. Is there a question? Or are we just hitting buttons by accident? I do it all the time. Okay. So you're in line at Chick-fil-A. There's 8 people in front of you. And the space between you and the person who's going to take your order is 54 feet. How many meters is that? That's our question. 54.0 feet is equal to question mark meters. Now I've already given you the equality. That's something that you will not be able to find on that chart with the prefixes because it's a metric to English conversion. Anytime you need to do one of those, you'll have the information. It'll either be on the equation sheet for the exam or it'll be given to you in the problem. So you don't have to worry about trying to memorize any of those. But after we have the equality, we need to write conversion factors. Does anybody remember how we write conversion factors? If you do, you can either write one in the chat or say what it is. We covered this last week. If you don't remember, you can just let me know that too. Is this thing on? Y'all here with me? Okay. I was feeling real lonely for a minute. Okay. Yeah, it's all right. Sometimes Blackboard will like take a minute. Remember that the conversion factors look like fractions. So we're going to take the 1 meter and put it over 3.28 feet. That's one of our conversion factors. The other one is the reciprocal. 3.28 feet over 1 meter. So let me know if that rings a bell for anybody. Hopefully this isn't completely new. Okay, y'all working on the answer, see? I would say we could do it all together. But if you have an answer, you can go ahead and put it in the chat. So we got to set up that equation. starting with our 54 feet. We have to choose one of these conversion factors. Which one are we going to use to convert our feet to meters? A or B? A little bit of a mix. But it seems like we have more A's than B's. We're going to have to go with the A's on this one. So we want the feet in the denominator. We already have feet in the numerator. We're taking 54 feet and converting it to meters. And since we want to end up with meters in the numerator, that's where it needs to be in our conversion factor. Feet cancel out. We're going to be left with meters. When you put this into your calculator, you're going to take 54 and divide by 3.28. And when you do that, your calculator will give you a bunch of numbers after that decimal point. So 16.463 something, something, something. That's the calculator. But we can only have 3 sig figs here because 54 feet only has 3 sig figs. So when we write that with 3 sig figs, we end up with 16.5 meters. Okay. So we haven't done one like this yet, but the concept of figuring out how long it'll take to get somewhere is one that you probably can relate to. But let's do it together. If you end up with an answer or you want to just keep working at your own pace, that's fine. So the question again, we've got a pace of 65 meters per minute. We're trying to figure out how many minutes it'll take to travel 7.5 kilometers. So here's our plan. First, we have to convert the kilometers to meters. Then we can use our pace to go from meters to minutes. Let me know if that plan makes sense. Does everybody understand what we need to do for this problem? Okay. So for the first part of our plan, to go from kilometers to meters, we need an equality. What's our equality? If I've got 1 kilometer, how many meters do I have? Not quite. Yeah, it's the opposite of what you just said. You look up the prefix on the chart. K is kilo, and it's going to say 1,000 or 1 times 10 to the third. So that's what you fill in here. You fill in what the number is for that prefix. Then we write the conversion factors. So we can take our 7.5, and I'll do this in a different color so you can see it. And we can use one of these unit factors, or conversion factors, to go from kilometers to meters. We'll use the one that has kilometers in the denominator. Kilometers cancel. I've got meters. So 7.5 kilometers is the same as 7,500 meters. That's the first part of our plan. So we know that. Everybody good so far? For the second part of our plan, we need to go from meters to minutes. And at 65 meters per minute, we can actually write that as an equality. This equality is only good for this problem. 65 meters is equal to 1 minute. And we can write conversion factors. So does everybody get that part? The key here, I think, is knowing that you can write 2 conversion factors from the equality, and that this was given in the problem. 65 meters per minute. That means 65 meters is equal to 1 minute. And we can write the 2 conversion factors, 65 meters over 1 minute and 1 minute over 65 meters. That's the key, I think, to solving this problem. So let me know if you're still with me. Now we set up this part of the equation, and I'm going to do that in red. It'll make a little more sense once we finish it. And then I've got another problem that's similar to help you with the compound conversions. Now we're starting with our 7,500 meters, because that's what we're trying to figure out. How long is it going to take for us to walk this distance? Which unit factor am I going to use? I call it unit factor because other chemistry textbooks use unit factor. Y'all's is conversion factor. It's the same thing. We've got to use B. We're trying to get to time in minutes. So we have to cancel out those meters. Do that math in your calculator and let me know what you get. We need 2 sig figs here. So give me your answer with 2 sig figs. That's our calculator answer. With 2 sig figs, it's 120 minutes. Don't forget your units. How do we feel about that one? Let me know if you need to go over it again or if you're ready to try a similar problem. All right. If we're feeling good, then we'll try another one. So I did a similar question in the recorded video on YouTube. We've got a doctor's order prescribed a dosage of 0.150 milligrams of Synthroid. If tablets contain 25 micrograms of Synthroid, how many tablets are required to provide the prescribed medication? Okay. So we've got quite a few numbers here. We've got this 0.150 milligrams. That's what the dosage is that the patient needs. We know that one tablet contains 25 micrograms. And our question is, how many tablets do we need? So let's write a plan for this. This is another thing where we have to do 2 steps. We have a dosage in milligrams, but the tablets are in micrograms. Those 2 units are not the same. So we need to make one into the other. So what I'll say for my plan is first, I'm going to convert my dosage from milligrams to micrograms. Then I can calculate the number of tablets. Everybody good with that plan? Does that make sense? Okay. So the first part of the plan, we've got to go from milligrams to micrograms. We can't do that directly. We've got milli and micro. Those both have prefixes, so we can't just look at the chart and pull one number. But what do they both have in common? Milligrams and micrograms. They both have grams. So I can write two equalities that relates each of these to grams. So help me out. Let's fill in these numbers. What is 1 milligram? And then what is 1 microgram in terms of grams? Yeah, the milli is 0.001. And micro, which you may also see like this, but you'll most commonly in your book see the MC. That's for micro. Yes, thank you. We can write our conversion factors as usual, and we have to do that for both of these equalities. And that's all the work that we're going to do for now. So we've got our conversion factors ready to go when we're ready to put the equation together. Now let's do the second part of the plan. I'm going to make a little room for myself here. Box that off. And I'll do the second part in blue. We're told a tablet contains 25 micrograms. That, in and of itself, is an equality. And you'll have to be able to read a problem and see when you're being told what an equality is. So that is an equality. Does everybody see where I got that from in the problem? Now, this is something that takes practice. So when you're reading through a problem, you need to identify things that could be equalities or conversion factors that you can pull out as you're given information. We've got 1 tablet is equal to 25 micrograms. From here, all we have to do is write our conversion factors. I'm just going to abbreviate it as tab because tablet is just too long. Now we're going to put together the equation. We're starting with the first part of our plan, which is to convert the dosage from milligrams to micrograms. To do that, we have to use both of our equalities, and we've got to choose one conversion factor from each of them. We're going to go from milligrams to grams, and then grams to micrograms. So that's our goal here. This is the A column and the B column. To go from milligrams to grams, which one of my conversion factors do I need? A or B? Now, which one do I need to convert from grams to micrograms? So that's the first part of our plan. We've got our dosage in micrograms. Now we've got to figure out the tablet part. So we choose one of our conversion factors from here, and that's going to take the number of micrograms and convert that to tablets. So am I going to use the first one or the second one, A or B? Y'all know which one is which. Yeah, we're trying to cancel out the micrograms and be left with tablets. So that's A, 1 tab over 25 micrograms. So we just had to use 3 conversion factors to go from our dosage all the way to the number of tablets that need to be taken for this dosage. When you're putting this into your calculator, you want to be careful because you're doing multiplying and dividing. You're taking 0.15, multiplying by 0.001, then you're dividing by 1 times 10 to the minus 6, and then you are dividing by 25. Every time you see a number in the top, the numerator, you're multiplying. Every time you see a number in the denominator, you're dividing. Put that into your calculator and let me know what you get. Putting in those exponents can be a little bit tricky. And to make sure that you're getting it in properly, you may want to just use parentheses around it. You don't have to do that for all calculators. You got the right number, 6, so it should be 6 tablets. and we need to use 2 sig figs because of the 25 micrograms. Yes. Mm-hmm. So that's a little bit more of a convoluted way to do it. But if that makes sense to you, yes, that is fine. Yeah, it wasn't as straightforward as this method, but if that makes sense for you reliably, then that's what you do. I'm not here to tell you that you have to do it my way. I'm here to show you a way that works, that I know, and I can compare what I do to what you do to say, yeah, that works just fine too. No problem. So you should get a whole number and it should be greater than 1. It shouldn't be like times 10 to the minus 12 or anything like that. So that's a calculator thing, figuring out how to do that. And if you need help with your calculator, Google is helpful. But also, I may be able to help you in office hours or something like that. So you can always reach out. Or if you know somebody who uses your same calculator, you can ask them. So if you didn't get the right number answer, but you understand how we got there, you're in a good place. So talk to me about this one, because this one was probably, this is the most complex problem that we've done so far. Yeah, you've got to take your time. I've been doing this for a lot of years, and I still sometimes make mistakes just because I'm trying to move too fast. So take your time and really think about what it is you're doing without the numbers. I think the numbers kind of make you do things before you really know what you're doing. You can put whatever you want into your calculator, but it doesn't have to actually make sense for solving the problem. So take it slow and think about what it is you need to do and what units you're trying to end up with. And that'll help. Let me know if you have questions or if you're ready to move on. It may take a little bit for this to kind of sink in. I'll post some practice problems and give you some practice next week. For our do now, we'll do a little bit of exam review. So if this is still kind of shaky, don't worry, you'll have time to practice. So can we move on? Okay. So we're still doing conversions, but now we're moving over into percentages. And we can use percentages like conversion factors. In this problem, we're told that a person has 18% body fat and that they have a total of 21.6 pounds of fat. How much does the person weigh? 18% body fat we can write this as a conversion factor. When we're saying 18%, what that really means is 18 out of 100. We already know this. We've been in school. You've been in school pretty much your whole life, starting with kindergarten, maybe even pre-K, all right? You know what percentages are. You get grades. But how do we take something like 18% body fat and make it into a conversion factor that's a little bit more helpful? Well, if our question is asking about, okay, well, we've got 21.6 pounds of fat, then that means that if you have 18% body fat, 18 pounds of fat out of 100 pounds of body mass or body weight. That's what that 18% means. Is everybody with me so far? Because you will need to be able to read a problem and write something like this. Now that we know this conversion factor, we can write the reciprocal. That's how we get conversion factors from a percentage. Now we can actually answer the question. So here's our equation. I'm starting with 21.6 pounds of fat. I need to use one of my conversion factors to get to the person's weight. Which conversion factor will I use, A or B? I'm going to use B. I know how much fat. I can cancel that out and get body weight. But be careful here. Notice that there's a number in both the numerator and the denominator. So when you put this into your calculator, you're taking 21.6, multiplying by 100, and dividing by 18. You have to do both. Our units cancel out. Fat cancels out with fat. We're left with pounds of body weight. But the numbers do not cancel. So make sure you put into your calculator 21.6 times 100 divided by 18. Let me know what you get and use the right number of sig figs. Your calculator will tell you 120, and this is one of those rare times where it gives you the right number of sig figs. The 18% has only got 2 sig figs. 21.6 pounds of fat has 3 sig figs. We can only use 2. Are we ready to try a similar problem? Go for it, Brandy. What's your question? No, 100 does not have two sig figs, but this 100 is an exact number because it's part of the definition of a percentage. Does that make sense? When you have an exact number, that exact number does not contribute to the number of sig figs your answer has. Okay. Now we ready to move on to another question like this? Great. This time we're talking about salmon. I like salmon. Literally had it like 2 nights ago. One of my favorites. Good for you. Can be a little bit pricey depending on what your budget is. But I put it in the broiler. Bam. 10 minutes. Perfect. Make a little rosemary lemon sauce. I be in the kitchen, y'all. My family eats well. Anyway, omega 3s, really good for you. Salmon is a good source of it. I'm sorry, I'm making y'all hungry. I'm making myself hungry. We gonna have fish again tonight. We have it like 2 or 3 times a week. This time it's gonna be cod though. Ooh, in the air fryer. I don't have one of those yet, but I've been eyeing an Instant Pot, one of those 8-quart ones, because I have a big family that comes with the air fryer. That just might be my Valentine's Day gift to myself. Yes. I'm going to do it. I'm going to do it. Yes. I've been like on that precipice, like, I don't know. Should I? Is it just a fad or is it really helpful? I'm going to have to go out and do it. Y'all just push me over the edge. Thank you. Okay. We're doing science and chemistry. Food is science. Cooking is science. That's why it's great. So salmon contains 1.9% omega-3 fatty acids. How many grams of omega-3 fatty acids are in a 113-gram salmon fillet? We've got this 1.9% omega-3 fatty acids. That is our conversion factor. I will give you 2 minutes to set up the problem. I want you to write out what that percentage means and the 2 conversion factors that you can get from it. If you have time in that 2 minutes to go on and solve the problem, go for it. But I at least want you to get to writing those conversion factors. Try it for yourself. I'll check in 2 minutes. All right. So I'm not going to ask you to write your answer in the chat because it's a little bit cumbersome. If you really want to, you can. But I'll write it out. 1.9% omega-3 fatty acids, which I abbreviate FA. What that means with the percentage is 1.9 over 100. The problem is asking us about how many grams of omega-3s are in this salmon fillet. So we can say 1.9 grams of omega-3 fatty acids over 100 grams of salmon. That's one of our conversion factors. Then we have the reciprocal. So how do we do with getting that part? Because that's the key to these problems. Talk to me, y'all. How do we do? Or is it still question mark, question mark? So remember that a percentage means something out of 100. So 1.9% means 1.9 out of 100. Does that help everybody else out? Does that make a bit more sense? Because we're not done. We didn't solve the problem yet. We just wrote out our conversion factors. Okay. Yep, that's exactly where we're going. We've got 113 grams of salmon, and we need to figure out what that means in terms of omega-3s. We need to cancel out the grams of salmon, so we'll go with this first one. Always make sure that your units cancel. Now that we know when we do this, we're going to end up with grams of omega-3 fatty acids, you can put it in the calculator. Don't forget, the top number, that numerator, you're multiplying. The bottom number, you cannot forget it. Divide by 100, or else you will have a really weird number, very big. For this question, we can only have 2 sig figs. So try that in your calculator. Let me know what you get. So your calculator will give you a few extra digits. But with 2 sig figs, it's 2.1 grams of omega-3s. Don't forget that grams. How do we feel about this problem? Good, meh, hate it, need more practice? Let me know how you're feeling. Good. Okay. So we'll just need to do some more practice. I'll make sure that we have one of these questions as part of our review next week. So I'm making a note to myself now. Okay. Unfortunately, we have to keep moving. We've got a lot more stuff to cover. We also need to talk about density as a conversion factor. We also talked about volume by displacement in the video. I'll briefly talk about that here just to remind you so we can do this problem. But I'm not going to go into super detail. If you don't understand it just from my quick little review, you'll need to go back to the video that's already posted on YouTube. So a couple things. First, we'll talk about density. Density is mass divided by volume. If I have a small volume of space, how much stuff can I fit into that volume? That's what density is. For solids, the units are grams per centimeter cubed. For liquids, we'll use grams per milliliter. Now, for some solids, you won't be able to figure out the volume by using an equation, length times width times height. You've been doing that. You probably did it in high school, maybe in middle school with geometry. Some solids, you just can't figure that out. They're irregularly shaped. For that, you use volume displacement. You measure out some water in a graduated cylinder or some other kind of piece of glassware that you can measure volume reliably. You measure out a certain amount. You add your sample, and you read the level of the water again. The difference between the two is the equivalent to the volume of your solid. So in this picture, we're starting with an initial volume of 30 milliliters of water. You add in a sample, and now it's 38 milliliters of water. So to figure out that displacement, to figure out the volume of the solid, you take the final volume, which is 38, and subtract the initial. And that gives you 8 milliliters. Something else that I covered in the video that I'm not going to take a lot of time to go over here is that 1 milliliter is the same as a cubic centimeter. So we can express this as 8.0 cubic meters. Does that concept of volume displacement make sense? You take a sample, put it in water, the difference in volume is the volume of your solid. So yay or nay on that. Then we can move forward. Yay, I like it. In this problem, we're told the density of green jade is 3.33 grams per centimeter cubed. We place that sample in water and it causes a displacement of 8 milliliters. That's what we were just doing with the volume displacement. So we know that that 8 milliliters is the same thing as 8 centimeters cubed. What is the mass of the sample? This is where using density as a conversion factor comes into play. I'm going to use a different color here. 3.33 grams per centimeter cubed. That's our density. We can write that in two ways. 3.33 grams for every 1 centimeter cubed, because that's what that means. Or the reciprocal. 1 centimeter cubed over 3.33 grams. That's density as a conversion factor. Everybody with me so far? I know we're moving kind of fast, so if you need me to slow down, let me know. I go faster when I think you get it. If I'm wrong, tell me. Okay. I know y'all are probably trying to write stuff down too and take notes, so I'm trying to be sensitive to that as well. Okay. So you said you don't understand. Is it the conversion factor, rewriting the density, that you don't understand? Okay. Whenever you see something that's got units, something over something, that's a fraction. And what density says is 3.33 grams of jade fits into 1 cubic centimeter of space. That's what the density means. So I can take the 3.33 grams and the 1 centimeter cubed and make a conversion factor. Does that help a little bit more to write out what it really means? Good. That's what we're getting to. So we've got our two conversion factors and we need to choose one of them to convert our volume to a mass. So you're absolutely on the right track. Oh, using the wrong color here. Yes. So here we go. We've got 8 centimeters cubed. We've got to get rid of centimeters cubed and get grams. That means we want to use this conversion factor with centimeters cubed on the bottom. So you're multiplying 8 times 3.33. And that will give you the number of grams your sample is. Your calculator is going to tell you 26.64. But we can't have that many significant figures. How many sig figs can we have? Two. We can only have 2 sig figs. The 8.0 only has 2 sig figs. The density has 3. So that's density as a conversion factor. And we also covered volume by displacement. Talk to me. Do you have questions, or do you want to try your own problem? Okay. I think it'll be good for us to try one, and then we'll see how it goes. The key, again, is knowing how to write the density as a conversion factor, and then choosing the conversion factor to get from what you have to what you need. An unknown liquid has a density of 1.32 grams per milliliter. What is the volume in milliliters of a 14.7 gram sample of the liquid? This is your density. You write it as a conversion factor. Then you can write the reciprocal. From there, you can solve the problem. I'll give you 3 minutes, and then I'll check in. All right, I'm going to get started here. Feel free to keep working if you haven't gotten to an answer yet. And if you're stuck, I'll help you get unstuck. We're trying to figure out the volume of this sample of liquid, and we know its mass. We know the density, 1.32 grams per milliliter. What that really means is that 1.32 grams of liquid fits in 1 milliliter. Now that we've got our two numbers, and if it helps you to think about it this way, then write it out, or at least think about it. Then you can write your conversion factors. .32 grams over 1 milliliter and 1 milliliter over 1.32 grams. Those are the two conversion factors that we can get from the density. Let me know if you got this far, or if you were like, that still doesn't make sense to me. So let me know how you're doing with this part so far. Good. Now, if you don't have it, it's really okay to say that too. And if you don't want to say it in front of everybody, you can send me a private message or hang back after class, whatever works for you. So we've got our conversion factors, and we need to do the actual math. Let's set up the equation. Starting with 14.7 grams, I need to use one of these conversion factors. A or B? We've got to use B because we're trying to get to the volume. We can cancel that out, and we're left with milliliters. In the calculator, it's 14.7 divided by 1.32. Oops. So your calculator will tell you some long decimal number. But how many sig figs can we have for this problem? We can only have 3. So that 1 is going to be our last retained digit. You look at the 3, it is 4 or less, so we're just going to drop everything after that 1. 11.1 milliliters is our volume. So how does that feel the second time around? Let me know if it feels better, worse, the same. Okay. Exclamation point. I like that. Goods and betters. If it doesn't feel better, if it's still kind of shaky for you, again, that's where practice comes in. So we're doing the problems that are associated with 2.6 and 2.7 right now for your Mastering Chemistry homework. So we're finishing up Chapter 2. Then we're going to move into Chapter 3, which is not quite as bad. So let's keep pushing. And again, you can always ask me questions. Your Mastering Chemistry homework is due on Wednesday. So that means you can let me know if you need something Tuesday office hours from 11 to 1. Or you can set something up outside of that if you have class or you have to work or whatever. So just keep me in the loop. So that was Chapter 2. We finished it. We're moving on to Chapter 3. And now that we've got everyone who's likely going to sign in for class today all together, couple of logistical points. If you've seen your grades, I've started putting in grades for Mastering Chemistry. Mastering Chemistry is 40% of your grade. It's a big chunk. I can't remember exactly what it is for this class. It might be 40. It might be less. It's a big chunk, nonetheless. If you have already talked to me about having issues with getting Mastering Chemistry up front, don't forget to reach out again when you have your stuff together and you're ready to start working. I try to give a little bit of leniency for the first couple of assignments because I know everybody can't get their money right. Stuff happens. But the further you get behind, the harder it is to get caught up. I allow everybody a little bit of grace. So if you message me and you're like, Dr. Hefner, Struggle, struggle, struggle. Can I get an extension? I allow you 1 time of grace. So I may give you an extra few days or up to an extra week to get your life together and do what you can do. But that's it. So use it wisely. If you're like, man, I missed the mastering chemistry assignments and now I'm behind, I have a 0, I don't know what to do, I'll tell you what you need to do. Hang back after class or send me a message using course messages. If you don't know how to do that, then go back to that first live lecture that we had and look at the notes. It shows you how. If you send me an email, I may not see it right away. I checked course messages much more than I check email now because that's where most of the students are contacting me. So if you send me an email and you're like, man, why is she taking forever to get back to me? It's because you're not using course messages. So don't fear. Get that mastering chemistry set up and reach out to me as soon as possible. Once we get through chapter 3 and that first exam, if you haven't caught up and gotten into a good groove of getting your homework and quizzes done and everything else, it's really going to be difficult for you to get back onto that train. So please take advantage of it now while you can. Okay. Off of the soapbox. You know who you are. Reach out to me. Let me know where you are. If you see a 0 there and you're like, wait, I thought we talked. It's because we need to finalize. Okay? All right. Questions about mastering chemistry before we move into chapter 3? If you're typing a question and it's a long question, you can just do a flag on the play and raise your hand so that I know you're typing something. Because I don't see the little, typing dots or anything like that to know if anybody has a question. So if we're good, let me know and we'll move on to chapter 3. Okay. So chapter 3, we're talking about matter. The first thing we do is classify matter. Matter, the definition, it's just all the things. All substances are made up of matter, right? We can break that down further into pure substances and mixtures. I'm not going to go into all of the definitions yet. I have a little fill in the word thing coming up here. So if you didn't get a chance to watch the chapter 3 videos, we are skimming the top for the first few sections because that is really just stuff you're going to have to memorize and understand. So I apologize. We are going to move like a wrecking ball through this stuff where it's just, okay, you got to learn the definitions so that we can have more time to do the math on the back end. So matter, pure substances and mixtures. With pure substances, we've got elements and compounds. With mixtures, they can be homogeneous or heterogeneous. We've got examples of each of these. Copper, that's Cu, you find it on the periodic table. That's where you're going to find all the other elements. So if it's something that you recognize from the periodic table, it's an element. Compounds, we're talking about things that exist in definite ratios. Water is always H2O. If it's anything other than that, it's not water. Another great example is table salt, sodium chloride, NaCl. If it's anything else, it's not table salt. Those are compounds. And you can break down compounds into elements. With the mixtures, the homogeneous versus heterogeneous. Homogeneous means if you're just looking at it with the naked eye, you won't be able to tell that there's multiple things in there. With brass, it's a mixture of copper and zinc. You can't tell that just by looking at, say, an instrument that's made of brass or brass fittings on some, plumbing somewhere. You won't be able to tell just by looking. Another example of that would be salt water or sugar water. If you sit that glass of salt water next to a regular glass of water and then just left it there and somebody was like, oh, I'm thirsty, they might get salt water and they won't know it until they taste it, because you can't tell just by looking that there's salt in it. So that's another example of a homogeneous mixture. A heterogeneous mixture is something that you can see clearly there's more than one thing in here. They can be physically separated very easily. One example would be water and copper. So back in the day, when they had malls, like indoor malls for real, not these, walk around to all the different shops, not outlets, not a strip mall, but honest to goodness, walk inside, multiple levels mall. I'm from New Jersey. There was this mall called Seaview Square Mall, and they used to have a little wishing well where people would throw coins in. They don't have those anymore. One, ain't nobody trying to throw no money away. But two, people don't carry money anymore. You can't use Apple Pay at a wishing well. So, very outdated example. But that's the idea of the water and the copper. If you have water and coins like in a wishing well, that's a mixture. Another mixture example would be sand and water. So I gave you kind of a drive-by of the examples of these, okay? What I'm going to do next is we're going to move on to the fill in the blanks. I'll give you a couple of minutes to read through these and try to place these vocabulary words. You will need to know all of these definitions, not just to pick out, okay, this means this, but to apply it. Which one of these is a heterogeneous mixture? Which one of these is an element? So this is just to kind of catch you up if you didn't get a chance to see the YouTube video. I'll give you a couple of minutes, like I said, to read through, and then I'll go through and fill it in. All right. So I'm going to go through these. The definitions that are here are the same ones listed in the YouTube video that's already been posted. So if you're like, wait a minute, I don't remember any of these words from the last slide. That's why. I kind of gave you try to cram in a little bit here to jog your memory type of definitions. And then I've got the official ones here that I'll fill in for you. So number 1, we're talking about something that has a fixed or definite composition. That is a pure substance. So I'll try to kind of recreate our tree here. So that was pure substance. Number 2, we're talking about pure substances that contain only one type of material. That's an element. For number 3, in a blank, the composition varies from one part of the mixture to another. So it's got to be a mixture. There's a hint. And the composition varies from one part to the other. So that's going to be heterogeneous. Number 4, contains 2 or more different substances that are physically mixed but not chemically combined. That's a mixture. When you think about that salt water example or the pennies in the wishing well, they're not chemically combined. They're just physically mixed. If you took that salt water and you just let it sit, eventually the water would evaporate off and you just have the salt. Or you can heat it and do the same thing. For number 5, in a blank, the composition is uniform throughout. Uniform throughout, that should immediately ring a bell for homogeneous. And then the final one contains 2 or more elements in a definite ratio. That is a compound. And remember that these notes will be posted on Blackboard, so you don't have to jot everything down. You can just check that. But you will be responsible for these definitions. Does everybody understand what they need to be responsible for so far? Okay, good. The next part of Chapter 3, we're going to cover states of matter and properties of matter. Now, states of matter, I'm sure you're familiar with: solids, liquids, and gases. But there are some characteristics of those states that we're going to talk about. And then we're going to talk about some other vocabulary words to talk about properties of matter. For Chapter 3, I really like the tables. The tables summarize all the information that you're responsible for that you need to apply. When we're talking about the 3 states of matter, solid, liquid, and gas, these are the characteristics that we care about. Well, up here. Let's try that again. Those are the characteristics we care about: shape, volume, arrangement of particles, interaction between particles, and movement of particles. Then there's examples. So, we're in college. I'm not going to sit here and read this table to you because I know you can read. You will need to know the characteristics for solids, liquids, and gases in each of these categories: shape, volume, arrangement of particles, interaction between particles, and movement of particles. Be able to answer multiple choice questions about these things. Does everybody understand what they are responsible for with solids, liquids, and gases? Okay. I'm really leaning on y'all to do this part because it's memorization. And I don't know about you, but in class, I don't want you to just be reading to me from a table. I'll fight you. I can read. Help me do math. Help me understand a concept. Don't read to me from a book. It's not story time. So if you do want story time, let me know. But you see how passionate I am about that. I'm like, look, I know y'all can read. That's not what you're here for. So let me know now. If you want me to go through the table, I can. But if you're good with me saying, okay, this is the kind of thing you need to know, and then we move on, let me know that too. So if you're ready to move on, just say move on. When talking about matter, we have to talk about chemical and physical properties and changes. This table summarizes what a property is versus a change when we're talking about physical and chemical properties and changes. It's a great table because you've got examples right here in the chart, along with kind of definitions. We'll do some practice problems to tell the difference between physical and chemical properties and physical and chemical changes. The key is understanding the difference between a property and a change. A property is just something that you can observe, right? It tells you the potential that something has. And I use the example of when you're looking for a house. So you may not be there, but maybe you looked at apartment complexes and you're like, child, I ain't living here. There's reasons for that. There's stuff that you've observed, right? Those are properties. Maybe the walls have a bunch of holes. Maybe you're walking through the hallway to get to that, one showroom that they have, and it smelled like garbage, and you were like, no. Those are properties. Things that you're observing, right? Physical properties. You're not changing anything about the apartment or the house. You're just taking note of what's there, what's around. A chemical property would be like, okay, I see this apartment. Oh, I can paint here. I see this color wall here. That's going to be my accent wall. I can put this furniture over here. My bed will fit there. That we're talking about the potential. That's a chemical property. What it can do. Does everybody get that difference between physical property and a chemical property? Okay. So what we're going to do now is go through these and classify them as a chemical or physical property. And in practicing, it'll help kind of reinforce the definition in your brain. Water boils at 212 degrees Fahrenheit. You can put a C for chemical or P for physical. Which one do you think it is, chemical or physical property? Sure, I can go back. Let me know when you're ready. Okay. A is a physical property. It's just something you observe about water. You're not making any changes to it, and you're certainly not talking about its potential to do chemistry. It's just, oh, water boils at this temperature. The wall is this color. It's an observation. Gasoline can combust. Chemical or physical property? It's chemical. Anytime you see can and then you see some kind of a reaction, that clues you in it's a chemical property. What about C? An avocado can oxidize. Yeah, that's a chemical one too. Oxidize. That's oxidation is a type of chemical reaction. So what happens with the avocado when that turns like that black color? So you made the perfect guacamole, you had some, you walk away for a quick minute, you say bye to your friends because this is post-COVID and you have people over your home. And then you go back inside and you're like, oh, this is gray. It oxidized. So the air, the oxygen in the air reacts with some of the compounds in the avocado and it makes it turn black. It still tastes okay, but it looks sad. See, chemistry is everywhere. What about D? Lead 2 chloride is insoluble in water. It's a physical one. We're talking about solubility. That's just an observation. I think we did pretty good on that. Now we're going to look at these changes and classify them as a physical change or a chemical change. A, we've got toasting bread. Is that physical? You could put a P, or chemical? Put a C. We've got a mixture. This one is actually chemical. When you're toasting something, you're using heat to make changes to the, in this case, carbohydrates on the surface of the bread. So you are changing, you're like caramelizing sugars and doing all kinds of reactions on the surface of that bread. And if you think about it, the taste is different. If you just pick up a slice of bread and take a bite, then you toast a piece and take a bite, it tastes warmer, right? There's more complexity there. That's chemistry. Let's look at B. Water evaporating in the hot sun. Physical or chemical change? This one is physical. We're not changing the properties of the water. It's just a change in state. It's going from liquid water to evaporating and being water vapor. Still water, just a different form. C. Slicing a pie. Physical or chemical? Yeah, it's got to be physical. Ain't nothing chemical about it. Although, those canned pie fillings, all types of chemicals. It don't even taste like real fruit. I just can't. So, oh, I baked a pie. You dumped a can of something into something that you pre-baked from the store. You didn't bake a pie. You assembled it. Anyway, that was a little bit mean. But I am really like, please, don't invite me over for no pie that you just dumped a can into something else. That's just, I'm offended. At least be honest with me. Hey, I'm throwing some stuff together. You want to chill? Sure. I might bring something to the party. But if you invite me over and say, I got you, made a meal, look at it, and then I see all the cans in your recycling, I'll be like, I ate already. I'm sorry. I'm not hungry. Do you have bottled water? Bottled water. Yeah. That's just me. I'm too grown to be enduring things I don't like. I hope y'all get there one day too. Anyway, we're doing chemistry. I think the biggest one we had a problem with was A, toasting bread. So toasting, roasting, any type of cooking, that is chemistry. Remember that. You'll see those on your homework and in the exam. Now we're moving on to another familiar topic, temperature. I'm sure that you've heard of the Fahrenheit scale. We use it with weather, cooking, all that good stuff. You've probably heard of Celsius too. We don't use it in this country. Everywhere else does, but that's fine. Kelvin, however, you may not have heard of unless you remember it from chemistry or physics. Kelvin is a little bit different because it is an absolute temperature scale. So when we say 0 Kelvin, and notice there's no degree sign, it's just Kelvin, that means that there is no energy, there's no heat, no nothing. Particles are at a standstill. 0 Kelvin is the absence of energy, absence of kinetic energy. With Fahrenheit and Celsius, you can have 0 degrees Celsius, you can have -10, -80, negative whatever number. That's because Celsius and Fahrenheit are relative scales. So know that difference. You're going to have to convert temperatures from one scale to the other. I've got a sample problem here, and I've got all of the conversion equations here. The top one, we're going from degrees Celsius to degrees Fahrenheit. The second one, we're going from degrees Fahrenheit to degrees Celsius. The third, degrees Celsius to Kelvin. And the fourth, Kelvin to degrees Celsius. Please note, you cannot directly convert from Fahrenheit to Kelvin. You must go from degrees Fahrenheit to degrees Celsius to Kelvin. With that said, let's try this sample problem, and I'll give you a minute, or probably 2 minutes to try it. Post-pandemic world, you study abroad in France. You meet someone, you make friends, and they're obsessed with baking bread. You get back to the US, you're like, I'm gonna make some baguettes. And then you're like, let me preheat the, don't know what 220 degrees Celsius means. I've got Fahrenheit. You need to convert 220 degrees Celsius into Fahrenheit. So before we break off, I've numbered these equations. Which equation do you need to use to convert 220 degrees Celsius to Fahrenheit? You can put it in the chat. 1, 2, 3, or 4. Yeah. As long as you can look at these equations and know which one you need, then you should be okay with plugging it into your calculator. I'll give you 2 minutes, plug it into your calculator, and let me know what you get in the chat. All right. So I'm going to write this out for y'all. We're looking for Fahrenheit. 1.8 times our degrees Celsius, which is 220 degrees Celsius, plus 32. To get the right number of sig figs, you need to break it down into 2 steps. You figure out what the 1.8 times 220 is. So you put that into your calculator, and that's 396. With sig figs, we can only have 2 sig figs. So 400 degrees doesn't have 2 sig figs, but we know that we need to. So we'll just keep a mental note. We've got 2 sig figs here. That's why I underlined the 0. Then you add 32. And remember, when we're adding, we line things up, and then we figure out, all right, how many sig figs can I have? With this one, I need 2 sig figs because the 400 has 2. I need to carry 2 over. So 432 becomes 430 degrees Fahrenheit. Now, if you just put it all into your calculator and you got 428, and then you said, okay, I'm going to round to 430 because this 220 degrees Celsius has 2 sig figs, you'll be in the right ballpark. And for multiple choice questions, that's going to be close enough. But I wanted to show you how your textbook would do it so that when you're doing it for your homework, you won't get caught up. So is everybody good on how to use these equations? Okay. Now we're getting into the more math part. Oh, okay. Yeah, I can go back for that. So with 396, if I wanted to have 2 sig figs with that, I'd be looking at the 9, right? So that would be my second significant figure. I look at the 6, it's 5 or greater, so I have to round that 9 up. But I can't go anywhere from 9, right? I've got to just turn over the whole number, which would be to 400. 400 doesn't have 2 significant figures, but it's not my final answer anyway. Your book would split up this calculation, yeah, and then the addition. So the multiplication, you do that, you get a number with sig figs. Then you take that number and add 32. Then you figure out sig figs. Okay. Yeah, those sig figs, they will get you. So what have we covered so far in Chapter 3? We've covered the states of matter, properties of matter. We've covered physical and chemical changes and properties. We talked about temperature. Now we're talking about energy and nutrition. So I kind of combine these two because they're related. If you want the definitions of a calorie and all of that stuff and kind of the details behind doing these problems, go to the lecture video. What I want to focus on is solving the math problems, and we can teach those concepts and definitions through actively doing problems together. This will help you see where you'll need the most help and where you should focus your studies on, what you might need to come to office hours for, versus taking the time to go through all the definitions and set it up all pretty and nice. So we're jumping into problems on purpose. If that style doesn't work for you, let me know. You can send me a message with course messages, or you can let me know in the chat or what have you, and I'll try to accommodate you. But because of our limited time, this I think is the most effective way for us to learn the material and get some practice together while you can give feedback. But again, this is your class, not just my class. So let me know if there's things that you need, ways things could be improved. I'm always looking for that. As long as you're kind. Don't be mean. I try not to be mean to y'all. So be kind. Constructive criticism, very welcome. Negative vibes, bad vibes, we don't do that. Okay, off the soapbox. Very much on that Chick-fil-A kick still. Let's talk about energy and nutrition. You can look at the nutrition facts and you'll see X number of calories. Calories from fat, that's energy. So if you're looking at Chick-fil-A sauce, it's got 140 kilocalories. That's the same thing. A kilocalorie is the same thing as that capital C calorie that you see on nutrition facts. And them little servings are small too. That little rectangular sauce, that you can inhale that by accident. But that's 140 calories, kilocalories. How many joules of energy does a serving of sauce contain? Joules, that's the SI unit for energy. So you'll see joules and you'll see calories. We can convert between the two because 1 calorie with a lowercase c is equal to 4.184 joules. Now, why do we have calories and joules? The little c calorie is based on properties of water and how much energy it takes to raise 1 gram of water by 1 degree Celsius. So that's what the calorie is based on. The joule is kind of more of a physics approach to defining energy. We're not going to talk about that one. So how do we do this? Well, this is simply a conversion problem. I have 140 kilocalories, and I want to know how many joules that is. We abbreviate that with just a capital J. 1 calorie is equal to 4.184 joules. That's an equality. But notice that I have kilocalories here. So I need to do 2 conversions. This is where our plan comes in. If you are comfortable to work ahead of me, as always, go for the gold. But if you're not, or you just want to see how I lay it out, stick with me. First thing we have to do is take our kilocalories and convert that to calories. It is very similar to what we've been doing with our conversions and the metric prefixes. So don't let the fact that it's calories or joules confuse you. We're still just looking at the prefixes and writing an equality. The second part of our equation, we're going to take those calories and convert to joules using the equality that we've already been given. For kilocalories to calories, if I have 1 kilocal, well, think about it. If I had 1 kilometer, that would be 1,000 meters. If I have 1 kilocalorie, I've got 1,000 calories. Is everybody good so far? We put out our plan. We have an equality to go from kilocalories to calories. Let me know if you're still with me. Okay. We write out the unit factors or conversion factors. There's that. Now we've got to handle calories to joules, which we've already told. We've got that in the problem. From there, we can write those conversion factors. Now we can set up the problem. $140 kcals. We need to use one of these conversion factors from our first equality. Since we're trying to get rid of kilocalories, we need the one that has kcals in the bottom. Now we're going to go from calories to joules. That's where our second equality comes in, and we choose one of those conversion factors. We're canceling out calories. We have calories in the top right now, so we have to use the conversion factor with calories in the bottom. For your calculator, that's what you're putting in. Go ahead and try it. And for this problem, we can only have 2 sig figs. 140 only has 2 sig figs. Your calculator will give you a very big number. Didn't show my unit cancel. There we go. With 2 sig figs, we're looking at the 8 as our last retained digit, which means the 5 will tell us if we round up or get rid of everything. 5 is 5 or greater, so we will round that 8 up to a 9. But we have to put placeholder zeros because 59 is not anywhere close to the number that our calculator gave us, 585,000. How did that problem go? It's a conversion problem, just using energy. And of course, we got so close.